Hello girls. Yesterday we started with chapter 7, Energy, Work and Power. We talked about energy. We said energy is the ability to do work. We have so many types of energy. We talked yesterday about kinetic energy and gravitational potential energy. We said kinetic energy is energy of motion, potential energy is energy of position. Okay? Today we want to talk about elastic potential energy. Elastic potential energy is a type of what? Potential energy. We have two types. We said gravitational potential energy, the one that we talked about yesterday, and the elastic potential energy. Look here please at this example to understand elastic potential energy. First of all, look at this figure. Here we have what? A spring. This spring has no forces in it. Okay? No forces on the spring. So this spring, we call it now, it is at equilibrium position. If you compress the spring, what will happen? A restoring force or force of a spring will generate or will appear to cause the spring to come back to its equilibrium position. Okay, so if you are pushing on the spring downward, the restoring force, it will be what? Upward, the opposite direction, because it wants to make the spring or send the spring again to the equilibrium position. Okay, this restoring force, it has a formula. It is K times X. We call this law Hooke's law. Okay? Force of a spring or restoring force equals K times X. What is K? K is a spring constant. Okay? It depends on the spring, and each spring has its own constant. And X is what? Is the distance the spring has compressed or stretched. And for example, here the spring, it is 20 centimeter. Then it is compressed. If I compress it, for example, 2 centimeter, this is X. It was 20. Now the new length of it here is 18. So what is X? 20 minus 18, it's the difference. It is 2 centimeter. This is an example, and when we solve, you will understand more. When a spring is displaced a distance of x and is subsequently released, the restoring force accelerates the springs back to its original length. Thus, displacing a spring has the potential to create kinetic energy. Okay? Now, girls, till now we are not talking about elastic potential energy. Till now, I was just explaining the restoring force. Here it's a force. Okay? This is not elastic potential energy. If we want to talk about elastic potential energy, here is the formula to find elastic potential energy. Now, when you start compressing the spring or stretching it, what you are doing? You are doing work on the spring. You are applying a force on the spring. So you are putting what? Energy on the spring. So the spring at this moment is gaining energy. What type of energy? Elastic potential energy. So here at this moment, the spring has no elastic potential energy. When do we have elastic? When the spring is compressed or stretched. In these two cases, we have elastic potential energy. Okay? So to find elastic potential energy, we use this formula. Half times K, you remember K, spring constant, times X. It is the displacement. X squared. So here elastic potential energy US, and it's measured in joules. K spring constant, it's Newton per meter, the unit of it, and the displacement in meter. Here's here, I just want you to understand. Displacement here, it's not the new length of the spring, okay? Displacement, it's the difference between the initial length and the new length. So you find the difference, you just subtract. Okay, that's what do we do here or here. Elastic potential energy is directly proportional to the spring constant and to the square of displacement. Elastic potential energy is a positive scalar. Okay, always the answer here will be positive because K, the spring, is positive constant, and here we have square, so always the magnitudes here are positive. Let's solve an example to find elastic potential energy to see how we uh, solve examples about elastic potential energy. The first one, a spring with a force constant of 5.2 Newton per meter. Okay, so you will ask me, what is a force constant? It's the spring constant, the same, K, 5.2 Newton per meter, has a relaxed length of 2.45 meter. What does mean relaxed length? It is the original length of the spring. When the spring is in equilibrium position, this is the meaning of relaxed length, okay? When a mass is attached to the end of the spring and allowed to come to rest, the vertical length of the spring is 3.57 meter. Look, the spring was 2.45 meter. After I attach a mass to the spring, what happened to the length of it? 3.2. So here, what do we have? Are we stretching or compressing the spring? For sure, stretching because the length has increased, okay? Calculate the elastic potential energy stored in the spring. Let's write the givens. First of all, here are the givens: spring constant, initial length, final length, and elastic potential energy. First of all, look at the figure here. Here is the original length of the spring without anything. This is 2.45 meter. The new length of the spring is what? 3.57 meters. So x here is x, girls. Okay, you subtract, you find the difference between the new length and the original or initial length. Is that clear? So let's start solving. Here is the formula. Half times 5.2 times what? We subtract the new length minus the original length, then we square it as in the formula. We find the answer is 3.3 joules. Okay? Okay, girls, this is how we solve number 1. Now, number 2, it's a homework for you. I want you to solve it by yourself. Let's continue. Now we want to talk again about mechanical energy. At the beginning of this chapter, we said that mechanical energy is the sum of kinetic and potential energy. So, total mechanical energy, sum of E, is the sum of kinetic and potential energy. Here is the formula for it. You can write it this way or you can write it this way. The sum of kinetic energy, mechanical energy equals kinetic energy plus potential energy. Okay? Great. Let's, before we solve this question, let's watch a video together about pendulum because it's very important in our lesson. Then we'll come back to this part.
A simple pendulum can be made by attaching a bob or weight to one end of a light rod and then suspending the rod from the opposite end so that it can swing freely and evenly from side to side. An everyday example of a pendulum can be seen in a grandfather clock. The pendulum controls the movement of the parts inside the clock. Once set into motion, the clock's pendulum swings so regularly that the clock keeps accurate time. The swinging of a pendulum is powered by an ongoing process of storage and transformation of energy. When the weighted end of the pendulum is raised to one side by an outside force, the system is given energy. At this point, the energy is stored in a form called potential energy. This means that the system has the potential to do work or to become active, thanks here to the weight's position high above the lowest point of its swing. Once the weighted end of the pendulum is released, it will become active as gravity pulls it downward. Potential energy is converted to kinetic energy, which is the energy exerted by a moving object. An active pendulum has the most kinetic energy at the lowest point of its swing when the weight is moving fastest. An ideal pendulum system always contains a stable amount of mechanical energy, that is, the total of kinetic plus potential energy. As the pendulum swings back and forth, The balance between the two types of energy changes constantly. At some points in its swing, the pendulum has more kinetic energy. At other points, it has more potential energy. Of course, no working system.
Okay, after that, let's solve this question together. I have here a pendulum. A pendulum initially at rest at point A. So it is at rest at point A. Is released and swings through points B and C. What types of mechanical energy are present at points A, B, and C? And what formulas could be used to calculate the total mechanical energy at each point? Okay, let's start. Here's a pendulum, okay? I told you before, the lowest point of a pendulum, we are going to assume it as what? The reference point or the surface of Earth, for example, here for gravitational potential energy. Okay? What does it mean? It means that at this point, we don't have gravitational potential energy. We have zero because there is no height. At any other point, there is gravitational potential energy. Okay? Let's start. A. What do we have? We have at point A gravitational potential energy only. Only gravitational. Why? Because they said here a pendulum initially at rest. This is number one because it's written at rest. It means no speed. No speed, it means no kinetic energy. And even if this sentence is not written, you have to know that at the highest point, this one and this one, kinetic energy equals zero, always, for pendulum. How to find mechanical energy? Now we know that mechanical energy equals what? Kinetic energy plus potential energy. Kinetic energy is zero, so we are going to substitute and to use the formula for gravitational potential energy, which is m times g times h. Okay, what do you think at B we have? Think a little bit before I give you the answer. At B, we have both. We have gravitational potential energy because we have height above the lowest point or the reference point. And we have kinetic energy because the pendulum here is moving. It's not at rest. From here to here, the pendulum is moving. So we have both. So we will use this formula. Half mechanical energy equals kinetic energy plus potential energy. So we substitute each formula and we solve. The last thing, at C we only have kinetic energy. We don't have gravitational as we said because this is the reference point. There is no height. So at C we have only kinetic energy. Mechanical energy equals half times m times v squared. Why? Because we use the formula for kinetic energy only. Okay, let's see this example. A ball has mass and speed, and therefore it has kinetic energy. What is the effect on the kinetic energy of the ball when its speed is doubled? I told you before, girls, always when I ask you what happens to a variable when I change another variable, what you have to do, write the formula. The formula for kinetic energy is what? Half mv squared. What's the relation between kinetic and v squared? Look, v is squared. So if speed is doubled, if I write here instead of v, 2v, what will happen? I will square it. So it will become 4v. So the kinetic energy will increase by 4. If I say 3, I increase the speed by 3. What will happen to the kinetic energy? It will increase by 9. Okay, that's how we solve these questions.